time and you know, how long it takes something to land and all that stuff. So projectile motion. All right, so we're just going to go through a few of these examples here and see if we can get that going, and then we'll get into the quadratic regression as well today. Pretty easy thing though. The regression is easier than the projectile motion. All right, so projectile motion. The good thing about it is that most of the time they're going to give us the equation that we're dealing with. We don't have to build it. So that makes this a little bit easier because we don't have to make up an equation. It's going to give us the equation for here. They give us the soccer ball is kicked in an upward velocity of 90 feet per second, and it follows this equation where h is the height of the ball and t is time in seconds. All right. So what they want us to do here is take that quadratic equation, and because the 16 is negative, we know that this thing looks like this. And you think about when you kick a ball, it follows that kind of path a little bit. Not always perfectly that shape, but it goes up and goes down, right? Because gravity. So when you launch something or kick a ball, shoot something, shooting a basketball is a good example of that. It follows that path. The height over time follows that path for sure. And what they want us to do here is take that equation and find some certain things about it. So A part says, how many seconds will it take for the ball to reach its maximum height? Where would the maximum height be for that picture? The very top. What is that place called? The vertex. So anytime we see something asking for a maximum height or a maximum or minimum, we know we're looking at vertex. So for A part, we're going to find, it says how many seconds, so we're going to find the x value of the vertex. What was the little formula to find the axis of symmetry or the x value of the vertex? Negative b over 2a. The only difference is instead of x, we got a t in there. It's the same thing though. It's negative b over 2a. So negative 90 over 2 times negative 16. So I'm going to do that. Negative 90 divided by parentheses 2 times negative 16. 2.8125. I'm going to go all those decimal places because that's not too far. 2.8125 seconds. So when this soccer ball is kicked in 2.8 or almost 3 seconds, it gets to its highest point, and then it starts falling down. All right. B part says, what's the maximum height? So what is that? Well, maximum is where? The vertex, right? T that we found on A part was the time that it took to get here. Then the height would be the y value that goes with that. So all we got to do is plug in that decimal in the place of t and work it out. Okay, and so I'm finding h of 2.8125. I'm writing out what we're doing here. We're going to use the calculator to calculate it. So I'm going to use my calculator to help me. I'm going to go to y equals, and I'm going to type in negative 16x squared plus 90x. Because that's what the equation was. I put an x's there instead of t's because my calculator uses x's. And then I'm hitting second table, and I'm typing in 2.8125. 126.56. And I'm going to assume that that's in feet. Feet per second, so yeah, that would be feet. Is the maximum height of that. If we wanted to do it, if your calculator won't let you type that number in, then you need to make sure that you're doing the table set thing and you've got the independent set to ask. So second tape and window, and make sure that's set to ask. If it lets you type it in, you don't have to do that. That's already done. But second graph lets you put a number in for that table. Okay. Now, C part is a little bit different. It talks about the domain and the range of the function. So because we're dealing with a word problem, the domain and the range of that function is a little bit different. What is the time when my foot hits the ball? How much time has passed in the flight of the ball at the point of impact when my foot hits it? Well, this thing follows the path of the ball after it's been kicked. So at time 0, at 0 seconds is when it starts following that path. So when I kick it, the time is 0. And then when does the time stop? When it does what? When it hits the ground, not at the top, because it's still in the air, right? It's following this path as long as it's in the air. So it's going to follow that until it hits the ground over here. So where are these two things at in relation to what we talked about the last couple of days? They're where on the graph? Think about the graph. The x-axis, because the x-axis is like the ground. When it starts at 0, goes up and comes back down and lands on the ground, that's the height of 0. It's on the ground. The height at time 0 is 0. We want to know what's the height or what's the time when it hits the ground again to get the domain. Domain is left and right, how long it's in the air is basically what domain is for this problem. So the domain is going to start at 0, and we need to find out where it goes to. Too far there. So I'm going to take that equation, negative 16t squared plus 90t, and set it equal to 0. That's saying, okay, when does that equal 0 height? When is it on the ground? How do I solve this? What would be one way? Say it again. Quadratic formula would work. Factoring would work easier, I think, with this one because I can get a GCF out of there. See, 90 and 16. Does 16 go into 90? Oops. 90 divided by 16. I don't think it does. Maybe it doesn't. No, it doesn't. I know 4 goes into 16. Does 4 go into 90? Nope. I know 2 does. So I'm going to factor out a 2. Negative 2t. That'll give me 8t minus 45t. Or 45, no t on that. And then I'm setting those equal to 0. So I'm using factoring by GCF to do this problem. So there's our t equals 0. We already knew that when the ball took off, time was 0. We talked about that. This is going to tell us what time it was when it hit the ground, how much time it relapsed on our stopwatch. So add 45, 5 and some change. Divide by 8. And since we're dealing with word problems here, I'm okay with decimals. Normally don't do decimals very much, but I'm okay with that on this because it's a stopwatch, doesn't have fractions on it. So 45 divided by 8, 5.625. So the domain for this one is going to be in the air from 0 seconds to 5.625 seconds. That's the domain. There's no way that the time can be negative, right? Because that'd be time travel, right? We can't go backwards in time. And once it hits the ground, it's not following this path anymore. The ball is just following this path as long as it's in the air. So once we get to 0, then that's where the domain stops for this problem because the ball's hit the ground. We know that it's a soccer ball and it's going to bounce, but it follows a different path after it bounces. Okay? It only follows this path until it hits the ground. Now, what's range when we talk about functions? All right. If you're dealing with statistics, it's the highest minus the lowest number. When we're dealing with a graph, it's the height of the picture. Okay. Where does the ball start? On the ground at a height of 0. Where does it reach the highest point? At the vertex. So we know that we got a y value of the vertex already. So the range for this one is going to be from 0 to 126.56 because that's as high as the ball got. And then it started falling toward the ground. The video, I just hit it. It's still going. Yeah, thank you. It has crashed a few times. It's working pretty decent today, so I'll keep an eye on it there. I hit it so you can still see my calculator screen well. All right. So vertex, anytime it says something about maximize or minimize, you know you're finding vertex. All right. Anytime it talks about hitting the ground or leaving the ground, you know that's where it's equal to 0. Those are the solutions or the x-intercepts. That's the idea with this projectile motion. Let's look at number 2 there. An apple is launched directly upward at 64 feet per second from a platform 80 feet high. The equation for this apple's height as at time t after launch is given by this equation. What is the height of the apple after 3 seconds? So this is an easier problem. We just got to know what we're doing with the equation and the 3. So what's the 3? It's just how many seconds it's traveled. So where does it go in the equation? In the place of t. It's a time, right? So we're going to plug in. We want to know what's the height after 3 seconds. So all we're going to do is plug in 3 for t and work it out. That's all we're having to do with this one. On that one, that's not bad at all. So h of 3, negative 16, 3 squared, plus 64 times 3, plus 80. And then ever how you want to work that out, I'm doing a little extra handwork here just because I'm kind of bored. 180 plus 12, I mean 192. But you could do this, negative 16, parentheses 3 squared, plus 64, parentheses 3, plus 80. And it's going to give you the height of that ball, or apple in this case, after 3 seconds, 128 feet. If they had asked us for the height of the ball after 6 seconds, what do we do? Plug in 6 and work it out. So this is actually easier today, I think, than what we've been doing the last couple of days. Especially when they ask it like this, we like those kind of problems. All right, let's launch a rocket here on number 3. A toy rocket is launched vertically upward from a 12-foot platform. And the initial velocity is 128 feet per second, the height, and they give us the equation. All of that stuff there in the first 2 sentences is useless because they've already given us the equation. If we had to build the equation, we'd have to know that stuff. But they built that. How long will it take the rocket to reach the ground? When does something reach the ground? At 0, right? When the height is 0. So what are we going to do with that problem? Set it equal to 0. I'm looking at that and I see 16, 128, and 12. We know all of those are divisible by 16 doesn't go into 12. 4 goes into 16. 4 go into 128. How many times?
32 times. So I'm going to divide everybody by -4 just to get rid of that negative that's in the front. And that'll give me 4t squared plus, or excuse me, minus 32t minus 3. That just makes my numbers smaller. I don't have to do that to work this problem, but it just makes my numbers a lot smaller and makes it easier to work out. When I look at that one, I see this big number in the middle and two small numbers on the outside. I don't even try factoring usually when it's like that. If I'm not going to factor it, how am I going to solve it? Quadratic formula. That's the way that I'm going to do that one. Is set it up with quadratic formula. So t equals 32 plus or minus -32 squared minus 4 times a times c, all divided by 2a. And I'm just working that out. 32 plus or minus, and then I'm going to use the calculator to get that square root thing going there. So parentheses, -32 squared minus 4 times 4 times -3. So getting that discriminant to be 1,072. And I'm not worried about getting an exact solution here. We're in the context of a word problem. It's looking for a time. Time doesn't happen in fractions. Time happens in decimals. We're using a stopwatch. It's going to have decimals on it. So I'm just going to get the decimal equivalent for the square root of 1,072. Okay. So square root 1,072. 32, and I'm going to go 2 decimal places there. 32.74. 32 plus minus 32.74 divided by 8. So I got 2 different answers that could happen here. I could have a time of 32 plus 32.74 divided by 8. And I could have an answer of 32 minus 32.74 divided by 8. Which one of those will disappear? Why? What's this going to be here? 32 minus 32.74. That's going to be a negative number. Can we have negative time? Do you ever figure out how to have negative time? I need more time in my day. Can you please let me know how to find it? Because I need some more time. 24 hours ain't enough to get everything done. So that one's going to go away. And all we got to do is just work out this side with a positive answer. And that's going to be 64.74 divided by 8, which is somewhere around 8. I don't know how much. 8.0925. So in about 8.1 seconds, our rocket will hit the ground. And it's done, probably. We busted it, most likely. Unless it had a... And then, guys, every semester when I go over this stuff, they talk about, well, what about the wind and all that stuff? We're trying to simplify this down to not including the wind. If you included the wind variable or some sort of parachute on the rocket, that when it reached the maximum height, it dropped it. Oh, it really complicates the math and doesn't work in an Algebra 2 sense. You'd have to involve a lot of physics equations that go with that. So we're not getting into that right now in Algebra 2. If you want to get into that, we need to implement a physics department here and start putting all that stuff in there. So we're trying to just simplify things and go from there. So here's things we've learned so far in the first 3 questions that we've done. Maximize or minimize, what are we finding? Vertex. Maximize or minimize is going to be a vertex. If it's asking for when something hits the ground or how long it's in the air, what are we finding? No, that's the vertex. The x-axis
the x-intercepts, the solutions, where the things equal to 0. All that's the same thing we did for about a week and a half, 2 weeks. Anytime they're asking for how long it's in the air or when does it hit the ground, we're looking for x-intercepts. That's what we learned from this. Number 4, look at that one. A penny dropped off an Empire State Building, which is 1,250 feet tall. The penny's pathway can be modeled by this equation. How long would it take the penny to strike a 6-foot tall person? No. We're trying to find when it hits a 6-foot tall person. So what's it going to be equal to when it hits them? 6 foot. If it asked for when it hit the ground, we said it equal to 0. But it asked when it hit a 6-foot tall person, which I'm not 6 foot. But we set the thing equal to 6 foot, right? So we set this problem equal to 6 because we want to know when it's going to hit this person in the head. Y'all ever watch Mythbusters? I love that show. It was an interesting show. I wish they still did it, but they may do it on like the Discovery Channel, or not Discovery Channel, but one of the science channels now. But they did a whole thing about dropping a penny off the Empire State Building because the rumor was that it would kill somebody if you hit them. They found out that through the turbulence of the penny falling, it couldn't hit somebody at the right angle to break the skin, so it wouldn't kill them. So just in case you're wondering, nobody's gonna get hit with a penny from the top of the Empire State Building and kill them. There's a thing called the Magnus Effect also that happens when you drop something off a really tall height and a stationary object. It pushes it out away from it. You've seen the Dude Perfect YouTube stuff when they try to shoot basketballs from top of Hoover Dam and stuff. It does that swoop thing, and that's what happens to the pennies there. But we're simplifying things here and saying it's following this path, and we're going to solve that. Now, here's where knowing different ways of solving equations is helpful and can make your life shorter. I would not do quadratic formula for this one. I would not do factoring. What's the other way that we solved quadratics? Square roots. So because it doesn't have a plain t term, that tells me I can do that. So I'm going to get t squared by itself.
Cameron Krauselman, report to the office.
So I'm going to subtract 1250. Negative 16t squared is equal to negative 1244. And divide by negative 16. And it doesn't matter if that goes evenly or not. I don't know my 1244 divisions, especially by 16. So 17.75. And I'm just going to use not 17, 77.75. And then I'm going to take the square root of both sides. Do I even need to take the negative side of that? Because remember when we did that in class, we always put that plus and minus in it. Why do I not need the minus side on this one? Never going to have negative time. We can't travel through time, can we? I wish we could. That'd be cool. I don't know if I want to or not, but ever seen Butterfly Effect? Yeah, that makes me wonder. So 8.82. We'll go 2 decimal places there. So it's kind of a long wait for it to hit that guy in the head. But almost 9 seconds for that penny to pop that guy right in the top of the head. If you got good enough aim, I don't know if anybody's got that. You just have to get lucky. All right, let's look at number 5. We're not going to do all of these. I'm just going to pick and choose here. And all right, fireworks are fired vertically into the air from the ground at an initial speed of 80 feet per second. The equation for the object's height as in time after launch is given by this equation. Find the domain of that function. All right, so domain. What do we do? This is an interesting one, I think. set it equal to 0 because we want to know when's that thing leaving the ground at time 0, and then when's it hitting the ground again. Now, I know it's fireworks. What do fireworks do? Usually explode. Yeah, most of the time don't hit the ground, but if they got a stick on them, that stick does hit the ground. So we're going to go by the stick travel. We shot fireworks last 4th of July at my in-laws' house, and the wind was kind of blowing, and so all of the shrapnel from the fireworks was landing on all our cars. So it was all over the tops of our cars for a day or so. It was nasty. It was fun though. We had a good time. All right, so we're setting it equal to 0. Negative 16t squared plus 80t equals 0. What's the best way of solving that? I could divide everything by negative 4, or I think actually 80 divided by 16 goes evenly, doesn't it? It does. So I'm going to divide everybody by negative 16. That's going to give me t squared minus 5t. And now it's getting a little easier. What would be the best way of solving this thing? It's a lot easier now. I think the best way is factoring by GCF. You could do quadratic formula and get the same answer, but I'm factoring by GCF because that's much quicker. Then we set each of those factors equal to 0. That's when it took off. That's when the stick landed on the ground. So our domain is from 0 to 5. When, in theory, should the firework have exploded? At what time? Where would that be? 2.5. Why? Yeah, it's halfway between, right? Yeah, because quadratics are symmetric. Remember that line of symmetry. So it should be halfway between if they've timed it right and the fuse is the right length and the right amount of powders in there and all that stuff. It doesn't always work that way, but those folks that design those things are supposed to set them up that way. That's what's supposed to happen. If you go to one of these larger displays, they really do the math to make that stuff happen. It's quite an impressive thing. All right. We're not going to do number 6. We're going to talk about it. They give us an equation, and the question they ask is, what's the maximum height reached by this ride? What are we finding? Vertex. That's all we got to do. And you negative b over 2a, plug that back in, you get the maximum height. Okay? I know how to do that. 7, jumping on the trampoline. Would Ava reach a height of 14 feet? Okay, if we find the vertex, what does that tell us? The maximum height. If that maximum height was greater than 14, will Ava ever reach 14 feet? If it is less than 14, no, she doesn't. Okay, so again, you could find vertex there and decide if she ever does reach 14 feet. That's one way to do it. I think that's the easiest way. What would be another way of determining if Ava ever got to 14 feet? Think about the Empire State Building problem. We're trying to drop the penny on the guy's head, so we set it equal to the height the guy's head was, right? So if we set that equal to 14 and solved it and got a solution that works that's not a negative number, then maybe she does get to 15 or 14 feet. But I think the vertex is the easiest way, and just compare the number on the vertex. I think that's the best way to work 7. But I'm thinking in terms of like ACT style problems, you don't always have to work it the right way to get the right answer. And I think the vertex way is doing that. It's the best way. All right, number 8. We got a diver. They tell us all this information, and the initial velocity The 10 goes right there. The 25 goes right there. So they didn't give us the full equation this time. Initial velocity, they tell us here in the description that V is the starting upward velocity. That's initial velocity. That always goes in front of the linear term. And then the starting platform is 25, so that's always going to go here on the C value of that. A part asks us to write that equation. So that's all we would do for A part is plug in the 10 and the 25. That's all A asks for. B part says find the diver's height after 2 seconds. What do we do with that 2? Plug it in for T and work it out. Just plug and chug is what we used to say. So yeah, put 10 in for V and 25 for S, and then put the 2 in the place of every T and work it out. Really easy math there. It seems complicated because it's a big word problem, but it's not that bad. All right, number 9. Talk about it. Astronaut going on the moon. They give us 2 equations. One is for the moon and one is for the Earth. It's talking about a baseball following a certain path. And it asks at the end, how much longer would the ball stay in the air on the moon compared to the Earth? How much longer? So what does that imply that we need to find? No. Time it's in the air, right? For each of those equations. So we would have to do 2 equations here. Set them equal to 0. I would do quadratic formula on both of those because they got decimals in them. I don't factor things that have decimals in them. So quadratic formula and find the time that it's in the air for each one of those. Okay, and then compare how long it's in the air for each one of them, and just subtract and see. The moon should be longer because the gravity is about what is it, 6/10 of what it is here, or no, it's a 1/6 of what it is here on the Earth. So you could work that out that way. So finding the x-intercepts is what you're doing there. Solution, set it equal to 0, solve it, that sort of thing. All right. Next thing in your little packet there is quadratic regression. And it won't take much to show you this. It is easy. And I don't think I've got those copied. So I'm just going to copy the T and the H from number 1. 0, 200, 0.5, 164, 1, 120, 1.5, 68, and 2, 8. They want us to find the quadratic regression for that. With the calculator is the way we do that. We don't do this by hand. So with a graphing calculator, what you're going to do is go on your calc. Y'all remember doing linear regression back? It's been a while, maybe February. It's been a while since we did that. You may not remember doing that, but it's the easy thing to do. We're going to hit the stat button, which is right there beside the little circle. Stat. I'm going to hit edit, and then I want to put my X values or my T values for this case in the place of L1. So to clear out L1, I'm arrowing up to where L1 is highlighted, hit clear and enter. And then I'm typing in those T values, 0, 0.5, 1, 1.5, and 2. And then on L2, I'm going to put those H values. Clear, enter. 200, 164, 120, 68, 8. Make sure you got the same number of X values as you do Y values. All right. Once you get all of those typed in, we want to tell the calculator to make us an equation. All right. So to get the calculator to make that equation, we're going to hit the stat button. We're going to go over to calc, and we're going to pick the quadratic regression, which is number 5. Should be number 5 choice. It's going to ask, okay, well, what's your X list? Well, we put that in L1. What's your Y list? We put that in L2. Frequency list, this should be blank. If you have anything there, go down there and hit delete and clear it out. It should be blank. The store regression equation, that takes several button pushes to get it to do that. Make sure that's blank because you can just write it down. And then we're just going to tell it to calculate. And what it's going to create is a quadratic equation that fits that data. AX squared plus BX plus C, that's quadratic standard form, what we're used to. And we use those as A, B, and C. So that equation is at negative 16 t squared minus 64 t plus 200. That's it built. That's how we build that equation. Once we get the calculator to build us that equation, B part there says how many seconds will it take it to reach the ground. So what do we do with that equation? No. That would be what's the initial height, where does it start at? We want to know when to hit the ground. When is the height on the ground? Or what is the height when something is on the ground? 0. So we're going to set the whole problem equal to 0 and solve it. It's just like what we were doing on the page in front of that. It's just we had to make the equation from that set of data first. Quadratic regression is all that is. Number 2 is the same thing, except for B part asks, how long will it take it to reach a height of 150? So that set the thing equal to 150 and solve it. And the back side, they're all the same. You go, your process is hit stat, edit, L1 is X or T, L2 is Y or H. Which depending on what you're talking about. And then stat, calc, quadratic regression, number 5. And get the equation. It is very straightforward there. And it gets you what you need. And then from there, excuse me, you're trying to find what they ask. All right. So there's a few problems here, not many. There are only 7 on the practice for this. We can work through. All right, so working those, I'll get the key printed and put up here in just a second.